epsilon, I told you, you can determine Kolmogorov scales if you know epsilon, but epsilon requires measurements or direct numerical simulations, right? So in the absence of that, so this thesis became popular because of this particular slide here. It actually tries to quantify how to get epsilon also without doing any measurements or anything, just an analytical expression. So how to determine epsilon is the question here to get micro scales, right? And we also say this epsilon is in dynamic equilibrium, whatever the large eddy is transferring to intermediate being transferred to dissipative. So I should be able to compute epsilon according to the hypothesis. So the dissipation rate of this TKE epsilon purely on dimensional grounds is now proportional to U cube by L. This we already used when we formed wall functions, when we in many places we actually use this scale, epsilon is equal to U cube by L, but where we assumed what that L has to be, right? We use this mixing length kappa y and so on, right? And U we said it is U star, right? That was your epsilon wall function was U star cube by kappa y in many places. So now that is an assumption. In hypothesis we have to see what is this U cube by L, because this L and U has to be associated with the large eddies, right? The energy containing eddies. So this scale U you can obtain from what is called Q square, 1/3 of this Q square, and Q square is nothing but your Ui prime, it is statistical isotropic, right? So it is a sum total of 3 U1 prime plus U2 prime, U3 prime divided by 3, that is the isotropic velocity scale of the largest eddy, an integral eddy. So this capital L, what I have here, so this is what we call an integral length scale, that is physical. So if you have a flow, you can actually know what is this capital L. For example, if you have a turbulent jet, I can say the orifice diameter, the nozzle diameter is my integral length scale, and I will know what is that. So this is something physical that you can know, right? If it's a pipe flow, it's a pipe diameter, so that is something physical. But the hypothesis talks about something else. So it talks about this small l as the pseudo integral length scale, where it says the pseudo integral length scale of energy containing eddy. So this eddy contains the maximum energy. So there is an eddy whose length scale is this small l containing the maximum energy, okay, and that L you can obtain using this U cube by epsilon, and this small l approaches the physical integral length scale in the limit of high Reynolds numbers. In the limit Re tends to infinity, L becomes capital L, okay. So epsilon is now independent of viscosity according to this formula, right? I already used this. Epsilon is U cube by L. If I know the velocity, turbulent velocity associated with the largest eddy and the length scale of the largest eddy, I don't need to know viscosity. That is the idea here, independent of viscosity, because it is depending on the large scales, right? It is depending on U and it is depending on L, right? Large velocity scale, large length scales. So if you use all this, you can arrive at this particular formula. So how did I arrive at this? So now you can see that now eta is nu cube by epsilon 1/4. That's the formula we used. You can go back and see, that is the formula here. The Kolmogorov length scale is nu cube by epsilon raised to 1/4. So Kolmogorov length scale eta nu cube by epsilon 1/4. Okay. So now epsilon I know, which is U cube by L. So I can substitute here, nu cube by epsilon is U cube by L raised to 1/4. Okay. Now I would like to make Reynolds number here. So I have nu cube L by U cube, I will put L cube here and L cube here. raised to 1/4. So that gives me L raised to 4 by Re 1/4. So eta is equal to 1 by Re raised to no, did I miss 3/4, right? 3. This is Re cube. Yeah, Re cube here. 1 by Re, or I can say 1 by Re 3/4 L. Therefore, you have got the formula eta by L equal to 1 by Re raised to 3/4. Okay, so now I can know the scale separation just by the hypothesis that if I assume the small l to be capital L, right, because I don't have access to this infinite Reynolds number. Let's say whatever Reynolds number I'm taking is very high. If I'm going to assume, then I know its length scale, I can assume it as capital L. That is my assumption. And then eta I can compute by simply knowing the Reynolds number, right. So I can compute eta by simply knowing the Reynolds number of your given flow and assuming a pseudo length scale. Let's say you can assume it as, this is for your own benefit I am telling you, not according to hypothesis. If you assume that this is same as your jet diameter or pipe diameter, whatever, I can now compute what should be the eta. And if you want to study turbulence, you need to capture all scales of turbulence. So at least now I know what should be the smallest scale. So you should know what should be the mesh size. So in your calculation, you will know the mesh size, or if you are doing experiments, you should know what should be the resolution of your experimental apparatus to capture eta, right. You must capture the eddy of size eta, right, both in numerically as well as in the experiments, if you are able to do that. Okay. So the Kolmogorov hypothesis gives you this ratio eta by L, which goes like this. This we later see that actually creates a big challenge when we actually do eddy resolved simulations, because if you take very large Reynolds numbers, the separation is larger, that is the difference between L and eta becomes bigger and bigger as Reynolds number is increasing, and that means you need to have a very tiny and tinier mesh to capture higher and higher Reynolds number flow, which becomes complicated and becomes very difficult for making a computation. You require very large computational resource for that one. Okay, is this clear so far? The three statements and its assumptions, and how using those three statements we can arrive at this formula where we can compute the Kolmogorov length scale eta by simply knowing the Reynolds number of this flow as well as the pseudo length scale. The length scale you can assume it as the integral length scale for your own benefit. Okay. So now what about the reality? This is again a general inference. So we have to always remember the basic assumptions here, that it is fully turbulent, the statement, but Kolmogorov changed the hypothesis in the 1963, where it considers what is called intermittency. So intermittency means that, let's say you have a turbulent jet, right, and then let's say you have a turbulent jet like this. So if you put a probe here, this will show a fully turbulent signal, and if you put a probe here, it shows a laminar signal, ambient, let's say, assuming it's laminar. But somewhere if you put it here, let's say, so at this time it is like this, at the next time instant, because turbulence is three-dimensional and temporal, unsteady nature. So the probe sometimes hits turbulence, sometimes it hits laminar flow. So that signature at this particular probe here, okay, if I plot it, it will be like some burst of energy and so on. But the probe here, this will show only a signal like this. Okay, so this particular probe will show what is called this intermittency. Turbulence is intermittent. So that intermittency nature, that means this fully turbulent has been corrected in K63 hypothesis, that it also takes into account the intermittency effects. But this question of high Reynolds number is still open for discussion. How high Reynolds number I need to go to actually prove or disprove Kolmogorov hypothesis. Okay, because it has a certain universal nature in the assumptions, or the consequences are, it is saying universality is there, right? It is statistically isotropic, independent of flows. So those things you want to prove, you need to go at very high Reynolds numbers. So it's still open for research. And also the cascade. So if we today look into DNS PIV data, we do see the breakup of eddy, some large eddy breaking into smaller and so on. We do see that, but that progression where a large eddy breaking into a smaller one and then a smaller one and then we don't see that, right? There is a burst of eddy, one eddy breaks up suddenly into smaller eddies. Those things happen. Sometimes small eddies also can amalgamate to form a slightly bigger eddy. Those things we observe in both in the DNS data as well as PIV implying that experiments, particle image velocimetry. It uses a Doppler effect to measure experiments. That's anyway. So I can say this is just experiments. Both in DNS and in experiments, we don't actually see this kind of linear progression of breakup of eddy from large to small like this. So it's still, I can put a question mark on this. And this energy transfer definitely occurs between large and small scales. That does happen, that we have seen from data. But theoretically there are three possibilities. One is that there can be a direct transfer of energy from large to small scale, right? I mean, your parents can directly give pocket money to you. It need not be to your brother, elder brother or sister and then tell them to give it. That can lead to some dissipation. Okay, so they can directly transfer money to you. Yeah? That is a possibility. But there is the Kolmogorov hypothesis goes in this progressive transfer from large to small. So your parents will give it to your elder siblings and they will give it to slightly smaller siblings and so on. So by the time it comes to you, it should be in dynamic equilibrium. So there should be no loss because whatever is being given. But let's not go into economics. But yes, so the Kolmogorov hypothesis will go in a progressive transfer from the large to small. That is the cascade. And there is one more idea which came from another person called Kreighnan. He proposed what is called an inverse cascade, where how about transferring energy from small to large scales? Why not the small scale give back energy? This is debatable. I think it is being seen in certain flows, not in all types of flows. Maybe one or two problems you can actually see this, what is called an inverse cascade. So at least it challenges this universal theory from Kolmogorov, right? This what is called Kreichnan's inverse cascade. So it challenges this progressive transfer idea. Like sometimes you feel, I mean, if the economic situation is not good at home, you have little bit of savings in your piggy bank, you give it to your parents. That's like that. The smaller eddy contributing to the economics of the home, right? So it does happen, not all the time, right? Usually you are happy getting pocket money, not giving it back. Okay, so that's my take on the Kolmogorov hypothesis. And also this inertial subrange, I told you, right, where there is epsilon is in dynamic equilibrium between the largest and the smallest, the intermediate scale. So there in the inertial subrange, if you plot, this is a common, you could go and see that usually in turbulence research we plot what is called an energy spectrum. Okay, people want to see energy spectrum, associated with the scales, and it would probably look like this. This is in log plot. Okay, so logarithmic of energy E and logarithmic of, let's say, the wave number. K is wave number. A log plot, if you plot, you usually see this kind of a graph. Somewhere here, what you can L or L, whatever you want to call it, and then there should exist a slope here. This particular slope, let's say, this slope, according to Kolmogorov theory, the turbulence kinetic energy or the energy associated, this slope has to be like this, k raised to minus 5/3. If the slope is not like this, that means the hypothesis and your data is showing not matching with each other, and that is usually we see today that not many turbulent data matches this slope k raised to minus 5/3 slope is not matched. Something else will come. Even if it matches, only a small fraction of the spectrum matches it. Okay, we don't see this, and of course then we don't know whether this is high Reynolds number. Whatever data that you are producing, is it high Reynolds number? We don't know. That question is also there. Okay, so that slope has to be at this thing. So at what scales energy is actually dissipated? That is the question we have to ask, and my take is at all scales. Okay, all scales are perfectly capable of producing dissipating energy, but disproportionately at small scales. The smaller eddies are capable of dissipating more energy than the large one, so it is disproportionately large at small scales. And another question which is very important is eta, the Kolmogorov length scale, the smallest turbulent scale? Okay, the Kolmogorov length scale, eta, is this the smallest? Many actually believe that it is the smallest turbulent scale, but it's no, because our governing equations don't know anything about scales. Scales is not what we are introducing, right? But continuum approximation breaks down below eta, right? So, and therefore eta is the smallest dynamically significant length scale. It is not the smallest length scale, but dynamically significant for us. In the continuum world, it is the smallest length scale. So eta must be resolved in your numerical calculations, or eta must be captured in your experiments if you want the correct data, because eta is representing the dissipation. If your simulation or experiments is not capturing the proper dissipation, then you may have, in the numerical calculation you will have problems, because there is accumulation of energy inside your system. There is no proper dissipation occurring. Okay, so that is that actually rests the Kolmogorov hypothesis. Very useful idea for turbulence modeling, especially large eddy simulations and related techniques. This Kolmogorov length scale also we seek to capture this eta in direct numerical simulations also, but we do see that the eta coming from so then the question comes, the eta that is coming from this formula and the eta actually coming from, so I have this eta, right? So now I say eta is 1 by Re, what was it, 3/4 L. Okay, so this is the hypothesis, right, or can say a theory, and I can actually get eta mu cube by epsilon raised to 1/4, right? Let's say I am getting epsilon from my DNS data. Okay, actual I compute now. So now what is the difference between these two? Are they same? We see that this Kolmogorov hypothesis eta coming from there is usually conservative. That means eta, let's say the actual eta coming from DNS, let's say it is saying 10 micron, then the theory will say it is 1 micron. So it is more conservative. That is in general that I have experienced since I work on direct numerical simulations. So I have seen that the theory gives conservative estimates. The eta is much smaller than reality. but if you have epsilon, you can actually compute from this. But this formula is still useful for me because I can estimate my initial mesh size eta, because I would like to capture this in DNS. If I don't capture, then no point in saying that it's a direct numerical simulation. Okay.